Well, here we go with another aldol reaction video. Uh, this, by the word intramolecular here, obviously you can imagine that means two functional groups in the same molecule reacting with each other. Alright. Then you could have an aldehyde and a ketone, aldehyde and an aldehyde, or one of each. Doesn't really matter. The fact is that the OH minus catalyst is going to react with an alpha hydrogen, remove it, form an enolate, which then reacts with the other carbonyl group. All right, and because that happens, it has to cyclize. Now, the intramolecular reaction virtually always involves a condensation, simply because of the stability of the ring that you form. And the other thing about it is there's usually two sizes of rings that are formed preferentially over all others if they can be formed, and those are 5-membered rings and 6-member rings. All right, the most stable sorts of rings around. In fact, there is a reason why 5 and 6-member rings are most prevalent in nature, and that's because they're the most stable. You very rarely will see a 4-membered ring, 3-membered ring, or anything bigger than that too. So these are the most common sorts of rings that you can have. Now let me just ask you guys one question. Let's assume this molecule is symmetrical, because it is. If we show it in another form that I'm going to use later on, this is the same thing as this, hexane 2,5-dione, it's a diketone. Can you guys see here, how many different types of alpha hydrogens are there in this molecule? I'm going to put circles around the different types. I'll give you a clue, there's more than one different type here. Well, there are the alpha hydrogens on this carbon, which are the same as the alpha hydrogens on this carbon here. That's type number 1. There's also the alpha hydrogens on this carbon, which are also the same as the alpha hydrogens on this carbon. So therefore, overall, 2 different types of alpha hydrogens. They're both next to one carbonyl group, so they're both essentially equally acidic. The question you have to ask yourself then is, well, is this is this alpha hydrogen going to get removed, or is this alpha hydrogen going to get removed? Doesn't that mean there are 2 possibilities? Well, yes it does. What we're going to do is go through both of those. Alright. Okay, let's see if we can figure this out. And I'm just going to get rid of these labels here. You guys understand right now there are 2 different sets of alpha hydrogens here. Let's say, for example, that the OH minus removes let's say, for example, it removes this alpha hydrogen here. All right. Can we draw out the structure of the enolate that we would get? Well, let's just try and do that. We have our O minus up here, and then we'd have a really crappy drawing is what we would have. Let's try that again, but in something that makes a little bit more sense. Here's our enolate. Alright, that's a little better. Alright, so that would be the enolate that we would get, and then in theory the electrons would come down here. Now let's number our carbons here. 1, 2, 3, and 4. The electrons come down and they would attack the carbonyl group and kick the electrons onto the oxygen. Now let's be careful in seeing what happens here. It's carbon 2 that is the nucleophilic carbon. So carbon 2 has formed a bond to carbon 4. You've attacked one part of the molecule with another part of the molecule. What size ring have you formed here? If you link up carbons 2 and 4, you also link up carbon 3, which means you form a 3-membered ring. I'm going to try and draw it out the way the reaction would show. We have that here, and then we have the carbonyl coming off the top, and then we would have our O minus, and then this guy. Now that's a 3-membered ring. How likely do you think a 3-membered ring is to form? Well, exactly. Not very likely at all. So
What if instead this alpha hydrogen was the one that was to get removed? Alright? Let's just try and draw out the enolate that we would get in this case. Alright? We have our O minus, we have our enolate double bond. I'm going to draw out the rest of the molecule here. Alright. Now let's see what we can do in this case. Right. 1, 2, 3, 4, and 5. Alright. Now in this case, the O minus comes down. Remember, it's the carbon next to the carbonyl carbon that's the nucleophilic carbon. In this case, it's carbon number 1. So that comes down here. Kicks the electrons out into the oxygen. Now, let's be careful now. Carbon 1 formed a bond with carbon 5. That means we've linked up carbons 1, 2, 3, 4, and 5. In other words, we've made a 5-membered ring. Okay? Let's just draw this out. A 5-membered ring. Now, before we go any further, which ring size is more stable? Is it 5 or 3? Well, obviously it's 5. Now, I'm going to number these essentially arbitrarily. You could number them however you want to. I'm just going to number them so we know exactly what to put where. Coming off carbon number 1. Well, it doesn't look like I don't have anything coming off carbon number 1. This bond between 1 and 5, by the way, is the new bond that I've formed. What do I have, though, coming off carbon 2? Well, that is my carbonyl carbon. Coming off carbon 3 and 4, I have nothing. Now, what do I have coming off carbon 5? I have an O minus. But let's be careful here. Notice we have 1, 2, 3, 4, 5, 6 carbons here. Let's label that carbon X. It's the black or the blue sheep of the family. We haven't got that carbon here anyway, and it's coming off carbon 5, so that means it's going to be here. X. I don't know why I'm whispering like that, but what the hell. Then we have our water that we would have generated in our first step, exactly as we've seen before. So that will come along here, go over here, and essentially give us our aldol reaction product. Alright, now I'm going to take off the X here for the methyl group. Now, at this point, we know we are going to lose a hydrogen from somewhere. We're going to lose the OH minus because we're going to get the condensation here to form this product. So we could lose a hydrogen from here, we could lose a hydrogen from here. Both of those are next to the OH, but which one are we actually going to lose? Well, it's one that's going to get removed by a base, which means it's going to be an acidic hydrogen, which means it must be this one. If you can see, the hydrogen on this carbon isn't acidic because it's not next to a carbonyl group. So therefore, here's the OH minus. And this is just exactly the same as we saw in the video for the aldol condensation. Breaks that carbon-hydrogen bond, forms a double bond, kicks out the OH minus, and gives us our cyclic product. I can't forget the methyl group there. Crap, that looks really ballsy, doesn't it? Let me draw that again with a little bit more room. Okay, apologies for my artistic skills today. I should say artistic skills, really, because they're not very good. So there's our double bond, there's the methyl group, and there is the carbonyl. Our alpha beta, once again, unsaturated carbonyl. Except this time it's cyclic because we started off with a diketone or dialdehyde or di, whatever you want to call it, and underwent the cyclization. Alright. So whenever you have a situation like this where you can form two rings
one of two rings, it's always going to be the 5 or 6 membered ring that you form. Because also bear in mind here, if this is going to eventually turn into an OH, if this turned into an OH, and then we lost this and the hydrogen, we'd actually form a 3-membered ring with a double bond, which is even less likely. So something like this is definitely a big no-no. Alright? Usually the same for 4-membered rings as well. If you can form a 5-membered ring over a 3-membered ring, you'll do so. If you can form a 6-membered ring over a 4-membered ring, you will also do so. And there we go. That is the intramolecular aldol reaction.